Hey everybody, today I'm going to be discussing acceleration. Now anybody who's been paying attention to how cars are driven, how people walk, anybody realizes that we don't always move at the same speed. We frequently have to change how fast we're going, whether that's because we're coming up to a stop sign, because we see somebody that we know and we want to talk to them, or because we're trying to get away from something. All of those involve a change of speed, and that's what we're going to be talking about today in acceleration. Now, quickly, our objective today, you should be able to calculate speed, velocity, distance, and acceleration given the appropriate information. So there is going to be some things coming in from our last unit that we discussed, and that was the whole speed and velocity thing. And now I'm adding what happens if I change speed. So let's go ahead and take a look at things. Acceleration. Acceleration is a change in velocity over time. If something is accelerating, we can say its velocity is changing, and we can track that change as a form of acceleration. Now, there is an actual formula for acceleration that I'm going to very quickly show you. The written out version looks something like this. We're going to take our final velocity minus initial velocity divided by time taken. The way that you're going to see me write this in class is that I'm going to have delta V over t. This Greek letter right here is called delta. I'll go ahead and write that out for you. Delta. Delta means that I'm changing something. It's a Greek letter. We use it for a change in temperature, change in speed, change in direction. It just simply means delta. If you want to write this out as an equation, and I'm going to go ahead and put this up here, we're always going to take our final speed, or v sub f, velocity final, minus our initial speed, velocity initial. And then we're going to divide that by how long that change took place. So v sub f minus v sub I divided by t. So for instance, if a car increases its velocity from 0 to 12 meters per second in 4 seconds, my final velocity is 12. My initial velocity, I started at a stop, so that was 0. And it took me 4 seconds to do. 12 minus 0 is still 12, divided by 4. And we figure out that our velocity is going to be 3 meters per second squared. Now, why in the world is this per second squared? Because these up here are meters per second, and this is just seconds. So I'm going to wind up with 2 s's on the bottom. It means meters per second squared. What does this mean in all practical explanation? It means for the first second, my car is moving 3 meters per second. For the second of time, I'm now moving 6 meters per second. So I have gone ahead and doubled my time. For the third second, I'm now going 9 meters per second. And you can kind of get the pattern. It's adding to itself, which is why we've got this meters per second squared thing going on. Now, if I take a look at acceleration and distance, this is one of the more complex formulas I'm going to throw at you right away. And it's okay, just kind of take it in. We'll be working with a lot of different examples. But here's the way that this works. You can calculate the distance that something moves if all you know is how fast it's accelerating and how long it's been accelerating. And this is the equation. The distance that it travels, which is d, is equal to its initial velocity times time, or how long it was at that initial velocity, plus 1/2, or 0.5, acceleration, little a, times t squared. So if a car starts at a stop sign and accelerates by 6 meters per second squared for 5 seconds, how far will it have traveled in that 5 seconds? Let's go ahead and take a look at this. If our car starts at a stop sign, I'm going to go ahead and assume that initial velocity is equal to 0. So if I plug 0 in for initial velocity, this whole first term becomes 0, because 0 times anything is still 0. So I wind up with distance is going to be equal to 0 times t, and t doesn't even matter because it's going to be multiplied by 0, plus 1/2 at squared. My acceleration is right here, 6 meters per second squared. That's going to get plugged into my a value, and 5 seconds right here is how long I'm traveling. That's going to be plugged into my t value. I wind up with 25 times 6 divided by 1/2, and that should be 75 meters. Did I get it right? Hey, look at that. I got it right in my head. Not so bad. Alright, so deacceleration. The only thing you need to know about deacceleration is sometimes when you're using that formula v sub f minus v sub I divided by t, sometimes your initial velocity, v sub I, is going to be bigger than final velocity. And when that happens, your top number becomes negative. And so you wind up with a negative acceleration overall. Negative acceleration just simply means it's slowing down. And that's really all you need to know. If you've got a larger initial velocity than final, you're clearly slowing down. This means that your acceleration is going to wind up being negative. So, quick questions that I want you guys to answer in your notebook. How is velocity different from speed? And the second one, if a car is traveling at a steady speed, what is its acceleration? And we'll be going over similar questions to that in class, but please try to answer those in your notebook. So, in summary, we talked about acceleration being equal to velocity final minus velocity initial divided by time. And I also gave you a formula for distance during acceleration, which was velocity initial times time, make sure I dot my I, plus 1/2 at squared. And this is usually a really easy thing to solve because anytime that we're starting from a standstill, velocity initial is going to be 0 during most of our equations. So, that is the summary of acceleration, and I will see you guys in class.